Theorem, and I'll give you a little bit of the history of the shell theorem. So Edmund Halley, the Halley of Halley's Comet, went and asked Newton what type of trajectory, or what type of, how basically planets orbit the sun. And and Newton answered him, it's 1 over r squared. Which probably means that Newton probably found that from a paper at some point. Because Halley was kind of blown away, like, what do you mean 1 over r squared? Like, how does that show that? And so then Newton went to work, and I think it took him about 20 years.
Question.
Yeah. No, totally unrelated. It's just, so Newton withheld the publishing of his theory of gravitation until he could actually show, which I think is the really fundamental result, which is if you have a spherical body, like the sun, right, and you have, let's say, the Earth, that the force of gravity behaves how? That is purely proportional to 1 over the distance squared between what? Their centers. That's right.
Use it or prove that it was their centers?
Yes, and this is the shell theorem. Yes. So in other words, notice this is a volume, right? So really what that's saying is that if I have this mass here, right? Notice this mass is closer to this than this side of the mass, right? That irrespective of the fact that this side is closer, the force of gravity strictly depends only on the distance between the respective centers. So the version of the shell theorem that I'm going to prove, and I'm going to prove this for... You'll see. The version I'm going to prove is the one that relates to electrostatics. Namely, you replace masses and instead you have charge distributions. So, let's hope I can remember this. So, let's start off by drawing out the objects. So here is... You're going to need to focus, guys. This is not going to be easy. It's probably going to be the hardest proof in the class. So the way I'm going to do it is I'm going to do it with respect to a spherical shell. So here's the spherical shell, and I'm going to do it with respect to a point. Because if I could show that the force from this shell, right, behaves in such a way that it's the distance between the center of the shell to that point, then by symmetry, what's going to be true? The other way around. In other words, that if this was some sphere, then it would act identically to a point here.
So right now we're kind of like just evaluating.
Yeah, we're evaluating electric fields in this case. So how are we going to do this? Well, clearly let's actually start off with our defined variables. What's going to be true over this shell? That it's going to have some type of surface area. Right? And so that means it has some surface charge sigma. And what is sigma equal to? Charge over surface area, right? So it's going to be dq dA. And now we have to figure out, and of course, let's say it's uniform. Make it uniform charge. So since sigma is uniform, we have that sigma is equal to the charge q over, what's the surface area of a sphere? Be careful. What's the surface area of a sphere? Think about it. That is the volume of a Four pi r squared. It's 4 pi r squared. So, and it's something that we should probably prove at some point. You should try to prove it based upon what you know. So how do you do this? All right, so I guess the best way to do this is to take some slice of this thing. So here's the center. What I'm going to do is I'm going to take some slice. Let me see if I can do this really. Yes. Very good suggestion. Okay, one. I'm going to actually use just freehand this. Okay. So that's my slice. All right.
That's like a disc.
This would be.
Oh, that'd be a hoop.
Not exactly a hoop. Yeah, I guess you could say it's kind of like a hoop. But we need to figure out what the dimensions of this hoop are. Because if you take a look, this I need to really. What's that right there? Right? And so then, what would this be? So let's take a look. So this, if you take a look, this angle right here, this whole angle is phi. So then this length is going to be what? What's that length, little arc length? R d phi. So this right here is R d phi. But if you take a look now, let's actually take this little slice. How does that little slice right there, just look at that little element. How does that little element affect that point there? Just this little sliver. This little sliver of charge, dq, is going to have an electric field pointed at this point in this direction. So now let's actually draw that. And can I change the color of this? Maybe, what color should I pick? Something like this? I'm gonna pick this color, right? And take that. Okay. All right, so you see that? Okay, so what is that? What is this length called? That's script R. So this is script R. Right? This is R. Okay? And I'm going to call this length little r. And notice this angle right here is phi. And that sliver, that little sliver of an angle is d phi.
Shouldn't like the other one be solid and dash?
Well, the whole idea here, let me fill this in. This thing,
Oh, okay.
okay, that's actually some ring. It's not exactly a disc. It's kind of a disc. Yeah, it's not a disc because it's hollow.
Oh, it is hollow.
It is hollow. Yeah. So what this looks like, if I turn this this way, what would it look like? What would you see? You would see a hoop or a ring.
But if you took like a small enough section, wouldn't it just be a loop?
Correct. Meaning if that d phi goes to 0, yes, it would just be a hoop. So let's actually look at what dA is.
Why can't you choose?
What's dA? So it's going to be, we have to think about what the radius is. We know what the thickness is. The thickness is r d phi. We know it's the thickness is r d phi. So now the question is, what is the radius of this thing when you turn it this way? It's this, which is r sine phi. Right? I'm taking this, and what am I doing? I'm rotating it in your view, and you see a ring like this that has a radius of r sine phi. So then what's the area? It's going to be 2 pi, right? It's going to be this circumference times that width. I'm looking for the differential area. So it's going to be 2 pi r sine phi times r d phi. Nice. Correct. So when you look at it, it looks like this. I want to, because, actually, no, what am I doing? Here it is. That's exactly what it looks like. Right? Notice, what is this? What is this here? What do you see here? You see a hoop. What's the radius of this thing? R sine phi. This thing. Right? Notice that's r. That's the radius. And that angle is phi. So therefore, that is r sine phi. That's this radius.
Oh, it's that height R sine.
That's right. Any questions now? Because this is the critical part.
Wait, but using that, what would R be on? Or like R's not shown.
What do you mean? Which R? Capital R?
Yeah, just capital R.
Capital R would be, if I found the center of this, it would be the center of this sphere to any point on the exterior. Which, if you look, the center is somewhere around there.
Yeah. Now I got you. Wait, I just have like a geometry question.
Sure.
So what you just did right there with the RDP,
Yeah.
that's like taking like the cylinder and you take the area times by the height.
Be careful. The RD phi is just that length right there. So in other words, RD phi, if I took this thing,
Surface area, not volume.
correct. If I took this thing and I drew a little, like, where's a Sharpie? Let's hope that the Sharpie can come off.
No, I think I get it.
Nice. Oh, well, that's, yeah, that's a. So if you take a look, probably will.
It will.
All right. So imagine this extends. Imagine this extends throughout, right, around the circle. You guys can see it. Come closer. Okay. So now the question is, what is that length? Right. So if you take a look, that angle is d phi, or delta phi. Okay. What's that? What's the length? It's r. So r d phi is this sliver right here. So what I'm finding is, what is the area of this ring?
The surface area.
Yes. What is the surface area of this ring?
The one line to the cutoff. Yeah. That whole section.
Yeah. What is the surface area of that ring? And so as you can see, it's going to be this length times the circumference. That thickness is this times the circumference. That circumference is 2 pi times the radius. That's the radius. That radius is r sine phi. Hopefully that was useful for you guys.
That was helpful.
Okay.
I just have a difficulty with d phi, that's all. Like what
D phi is this, if I look at this, an angle from the center to here. Right? That angle is phi. D phi is this small change in that angle. Because if you take a look, if I go from here to there, that's d phi.
All right, so d phi is the change?
The change in phi. And I really, I really want to stress this for the people who are starting calc this year. And even those that took it last year. If you find yourself memorizing calc, you're not learning it. You have to actually understand how things change with respect to one another to really understand what's going on. So, and this is kind of one of my central critiques of AP Calc, is that I think in generally any AP class, it will reduce to kind of some type of memorization chug.
Like last year's physics.
Yeah, like last. Yeah.
I mean, for most people in our class,
For most
they
people-
ended up just memorizing.
Yeah, it's just they just memorize, and it is what it is. Part of it's the age. So let's actually take a look at this.
Wait, Mr. Phil, quick question.
Shoot.
Can you help me learn how to tutor kids?
No, that's hard. That you're gonna have to learn yourself.
I have like so many like kids who are like seniors taking physics now.
Yeah.
Oh, you're a genius. Help me.
So anyhow, let's focus on this because we're not even anywhere near it. Let's focus. All right, so we have dA. Okay? So therefore dQ is sigma dA. Correct? dQ is sigma times this whole thing, which is 2 pi big R squared sine phi d phi. And so now we can begin writing the electric field, right? And notice what's going to happen. This is the electric field that's generated. This is the electric field. This is E script R that's generated from that sliver right here. So, but what happens when we look at the whole ring? The only component that survives is this guy, which is E little r. So now I'm going to zoom. Oh, maybe I need to zoom in. And I'm going to call this angle psi. Psi. Okay? And so therefore, ER is going to, or DER, let me make sure, DER, DE script R, is going to be DE script R times the cosine of psi. Nice. Now we can figure out what this is. So dE little r. What's dE script r? Well, dE script r is equal to dq over script r squared. Right? Times what? Times 1 over 4 pi epsilon naught. Right?
Wait, should there be another angle in there? Because you're only talking about a small chunk of that hoop, right?
No, now this is the hoop. This is the whole hoop.
Yeah. Okay, all right.
So now I'm going to zoom in a little bit. So DER is going to be dq over 4 pi epsilon naught script r squared. But this is equal to sigma, right, times 2 pi big R squared sine phi d phi. And that's over 4 pi epsilon 0 script r squared. Okay. Yes. Thank you. Thank you, Hyunmin. Times the cosine of psi. Very good. Because I was thinking the same exact thing, but in a different way. I was thinking, where's that other term? It's the cosine psi. So guess what we have to figure out? What the cosine of psi is. So, be careful. So, that's psi, right? Be careful. What is this length right here? So that's r cosine of phi, right? That's this thing right here. Yes. That's r cosine phi. This thing. Okay? So then I want you guys to tell me what cosine of psi is.
It's going to be r minus r cosine psi over script.
R cosine phi. Very good. In other words, it's going to be this length divided by script r. So let's find out what that length is. So we have the cosine of psi is equal to r minus r cosine phi over script r. Because I implicitly use theta, interestingly enough. Anybody know where I implicitly use theta? That angle. But I already integrated theta. Yes?
Why is it r minus cosine theta? Because that's the whole point is to prove that it's on the center of mass, not the edge.
Oh, we're not done yet.
Why, I don't get why we would, I know we're not done, but I'm saying why would we subtract r minus cosine theta?
Because take a look. This right here, right, is the length. Cosine of phi is this length over that.
Oh, I see.
But that length is not little r. Little r goes from the center to that point.
Yeah, I see.
So this length is going to be little r minus r cosine phi.
Yeah, it's going to come from the diagram.
Yeah, it's hard because the diagram's starting to get messy.
Okay, that makes sense now.
All right, so now, yes. I'm going to draw this. I'm going to draw this somewhere else, so that it's not as clouded. You don't have the ability to. You can, but one, we don't have it. We don't have it here.
No, I just use it for like graphics and stuff.
Oh, it's beautiful for
It
graphics.
doesn't have any of that snapping stuff that these smart boards have.
Yeah. But there's other issues. One is the high licensing fee.
What was that?
High licensing fee,
Oh, okay.
right? Remember, the school's not going to pay for that. Adobe Illustrator. Okay? And so this, if you take a look, right, this point, this distance right here, God damn it. Okay, that is little r. So this right here is little r. This right here is script r, right? This is big R. That's phi. So therefore, this length is what? This length is r cosine phi. And this is your angle psi. Yeah. So cosine of psi is going to be this length, right, divided by script r. But this length is r minus r cosine psi. So r minus r cosine psi over script r.
I thought psi was.
Phi, sorry. All right, so now, is that clear to everyone?
Yeah.
Okay. So, we continue.
Yeah, I just want to copy that down. Yeah, you have a ton of tabs.
I don't know how to group them up and delete them.
Just delete them if you want to. Delete on the computer, like after class, like today, because you're not going to need any of them.
Time is of the essence for Mr. Cooley.
It actually is.
You act like, you know, I leave at like 2:15 or like 2:30. I'm already leaving at like 7 p.m. So like going through this, most of the time I will go do this. I'll definitely do it today. But
You want to have to do it on Monday.
He's like, oh, very busy. He was just watching.
All right, so everybody have this? All right. So now, we have DER is equal to, and let's eliminate these 2 pi's, 4 pi's. So we have sigma over, what's that, 2 epsilon naught? And then I can take out the big R squared. And then what do we have? We have sine phi times this factor, r minus r cosine phi over script r. And then we have a script r squared, and then we have a d phi. Check it?
So you just plugged into that for the cosine and then canceled.
Yeah. Did a little bit of cancellation. I just plugged this in right here and did a little bit of cancellation. All right. Think about this. Newton did this
Good for him.
without, not only without a calculator,
You don't really
he didn't have variables.
Wait, what do you mean?
What?
What
do you have variables?
He didn't have variables.
do you mean by that?
Go read Principia.
Why wouldn't he just call it like angle A or something like that?
At that point in time, mathematics was written out.
Did he use numbers?
No, language.
He wrote it down.
Everything was based on geometry. You have to go read it. It's sick.
So you remember like
All right. So is everybody on the same page right now? Okay. Now we need to do a transformation, because what we need to figure out is how phi relates to R, script R. So how am I going to do this? I want to do this all in terms of R. So in order to do this, we need to go back to this picture. And the question is, how does script R relate to these other factors? Boom, boom, boom.
It relates to R. It relates to
What law can describe these relationships? Law of cosines. Law of cosines says script R squared is equal to R squared plus little r squared minus 2r cosine of the angle that's opposite.
Wait, isn't
So that's
that
phi.
R minus R cosine phi squared? And then the other one would be R.
No, be careful. I'm using the law of cosines.
Oh, you're using a little triangle, not a big triangle?
The big triangle, this guy,
The whole thing.
the really big triangle.
What is unlocked?
All right, you need to go back and review it, and you should try to prove it. It's in the summer assignment.
A squared equals B squared plus C squared minus AB, that one?
Yes, it's minus 2a dot b. You can prove it very easily using dot products.
Okay.
So now we need to figure out how R changes with phi. So how do we do that? We have to differentiate. So let's differentiate this. What do you get? So it's 2 script R times dr d phi is equal to those are constants, because we're only looking at how this changes with respect to sine phi, right?
Wait, what happens to the
Oh, what's the derivative of cosine? Negative sine, so it becomes positive.
R squared and those two.
What happened to those two? They're constants.
Oh, yeah.
So since they're constants, what's the derivative of a constant? 0, that's right. So everybody on the same page? How are you doing? That's chain rule. Chain rule says if I go and want to find the derivative of this, what do I have to do? If I want to find the derivative of this with respect to another parameter, I have to find the derivative of this function with respect to itself. In other words, I say let f of r equal r squared, right? So if I want to find the derivative of r squared, what do? I find what df d phi is. But chain rule says what? df d phi is equal to df dr dr d phi. What's df dr? 2 script r times dr d phi. And that's the derivative of this thing with respect to phi. So it's chain rule. So now,
Wait, is that implicit differentiation?
well, implicit differentiation is just another way of restating the chain rule. So let's take a look at this. What can we do? I can rearrange this, and I have that sine phi d phi is equal to R, script R over R big R.
You would do that so that you can integrate it?
Wait, script R dr. Sorry. Notice what happens to the 2's? Cancel out. Boom, boom. And so then sine phi d phi is equal to script R dr over little r big R. All right, want me to make it clear? No, because you need to understand that these are all radial vectors. And it's something you got to really... So does everybody have this relationship?
Yeah.
Let's go back. So what do we have? We have dE little r is equal to sigma big R squared over 2 epsilon 0. And then sine phi d phi, what was that? Script R over R little r d script R. Right? That's what sine phi d phi is. Then we have this 1 over script R squared. And then we have this term, R minus R cosine phi over script R.
Now we just not cancel.
And wait, we're not there yet. Because notice, what do we still have? We still have that cosine phi. All right?
DE is in terms of script R? What is DE?
What is DE? DE, right, is now, I want to integrate it with respect to script R.
Okay, yeah.
But I have to deal with this thing. So how am I going to deal with that thing? Well, let's follow what Zach said. Let's do a little bit of cancellation. So we have dE little r. You're not going to be expected to do this. But you should write it down because all the steps that are followed are really, really kind of killer. So what do we have? We have, I can cancel this with this, correct? So this becomes that, right? And then I could probably cancel this with this. And so then I have r, so I have a little r here, minus r cosine phi dr all over r squared. So now I'm going to go back. And what I'm going to go back to is this drawing. We're going to go back there. So, and actually, there's no need to go back to this drawing. I can actually go up here because we already stated this. So notice we have this script r squared, and this looks kind of familiar, right? Let's see what we can do. Let's go back here, and I want to take a look at this thing. Okay? So I'm going to copy this. I'm going to copy it, and I'm going to paste it right here. Okay? And watch this. So now r squared, script r squared, I'm going to write it like this. It's going to be r squared minus little r squared plus 2 little r squared minus 2r cosine phi. Does everybody see how that's true? What did I do? I added 0. Yeah, I just kind of cleverly expanded it. So So why would I do this? Well, consider this. Script r squared minus big R squared minus little r squared is going to equal 2 r squared minus 2r r cosine phi. Correct? Notice no difference of squares. I just subtracted it over. And then I'm going to divide both sides by 2 times little r. So I have little r squared, script r squared minus r squared over 2r. And what is that going to equal? You see the proof? Dude, Newton did this without words, without variables.
It's fascinating.
Just like, all right, so we got this now, right? All right, no, it's okay. It's so sick. I'll never forget when I first saw this proof. And I was just like, whoa. I was junior mechanics.
Okay.
All right, so we got this. So now, I think I could just take this and lasso it, copy it, go to the other one. And what am I going to do? I'm going to sub it in. I'm going to paste it first. Right? And so now, what do we have? Let me zoom a little in. Maybe a little bit. Maybe. There we go. Okay. So then what do we have? We have that dE little r is equal to what? We have a sigma big R over 2 epsilon 0 little r. Right? And then let's sub in this thing, which is script r squared minus r squared minus little r squared. Okay. And then we have a 2 little r. Correct? And then we have a d script r over r squared. Notice this is just getting to the point. We're right now at the point where we can begin integrating it. Okay. So we have dE little r is equal to sigma r. I can factor this out, right? We get 4 epsilon 0 little r squared. Ooh, all right. And, and now what? Then we have r squared d script r over r squared minus r squared minus r squared d script r over r squared. Notice what I did here.
Oh, you separated.
I separated the two terms. I factored out this 2r, I factored this out, right? And I broke this up. I distributed it.
Oh, yeah, you distributed D on
And you can see why I'm going to do this. Because what do I have here? That's a 1, right? And so now let's actually go start integrating. Yeah. And so now we have a sigma r over 4 epsilon 0 r squared, right? And then we have integral of d script r minus times the integral of dr over r squared. Now, what do we have to do? We have to think about what d script r goes from and to. So how are we going to do that? Well, best way to do this is to go back. Is everybody ready? Whoa, whoa, whoa.
Oh, just as a concept.
That's a constant, exactly.
What is the R squared?
Minus little r squared.
Well, is little r's gonna change?
Be careful. None of those.
Oh, okay. All right, yeah.
We're integrating everything with respect to script r. All right.
Why is script R changing, but not the angle?
No, the whole point is we've removed the angle now. Notice none of these parameters relate to the angle. That was the whole point of the transformation. So let's actually go. We're going to go back here. And notice, if you take this sphere, right, what is phi going to go from and to? Let's see if you guys can visualize this based on this. What is phi going to start at, and where is it going to end? It's going to start at 0, which is this, and go to pi. Why is it only going to go to pi? Because it's going to take this, and it's going to create, like, think of this circle right here, right? Remember this little sliver of area? It's going to take each one of those circles, right, and then basically wrap them around itself. Because this is already a circle, so you don't need to go 2 pi. You don't need to double up. All you need to do is take this and go 1 to 1.
Oh, I see what you're saying. Yeah, I got you.
I don't even know how to describe this. Like,
It's kind of like,
Just take like a disc.
and you kind of like,
yeah,
both it's like split.
yeah. Oh, actually, yes. Yeah. Where is it? Where is it? Where is it? Where is it? Here it is. Okay. Here it is. Okay. So you start off like this. How can I create a spherical shell with this? 180. Because every bit, yeah, it's just pi. It's going to go. So phi is going to go from 0 to pi. Phi goes from 0 to pi. So let's actually look at what script r equals at phi equals 0. Script r. Let me actually redraw it. Script r. This is phi equals 0. Script r would be this distance, correct? No, be careful. That's little r, right? This is...
Oh, when it's at 0.
So when phi equals 0, script r goes from, is equal to, at phi equals 0, it's going to be r minus r. What about when phi equals pi? It's going to be little r plus r. Because at pi, that distance will be So is that clear? So then our limits of integration are going to go from little r minus r to r plus r. Ready? So this is going to go from little r minus r to little r plus r. And this is going to go from little r minus r to little r plus r.
How come you can't take the minus r squared out?
It's outside of here, but that's 1 minus that times dr.
Oh, okay.
All right, so now, what do we have? We integrate this. We have sigma r over 4 epsilon 0 little r squared times what? When we integrate this, what do we get? dr. Integral of dr is script r. Evaluated from r minus r to r plus r. Minus script r squared minus r squared. When we integrate 1 over r squared, what do we get? Meaning it's going to be negative 1 over script r. Evaluated from Let's keep going. So this is equal to sigma r over 4 epsilon 0 r squared. And what do we get here? I want you guys to evaluate that. 2 big R or 2 little r? Sure?
No, 2 big R.
2 big R. Because r plus r minus r minus r. What happens to the minus? It becomes positive. Yeah. Minus. So this becomes positive. R squared minus r squared. And what do you get here? You get 1 over r plus r minus 1 over r minus r. Correct? Let me actually.
Can you explain why it changed to a plus sign?
Oh, it's just this minus sign, that minus sign.
Oh.
That's easy. Okay? So now, what do you see? You see sigma r over 4 epsilon 0 little r squared times 2r plus, well, what are you going to get here? Let's have a common denominator. What's that common denominator? So it's going to be r little r squared. So it's r squared minus little r squared times, and then we have little r squared minus big R squared, right? And what are you going to have in the numerator? Be careful.
Oh, because it's going to be backwards. So R minus R minus R. So negative 2.
Negative 2.
Big R. This is so cool.
All right.
'Cause those are,
But if you take a look at the denominator, what happens? What are these?
difference is squared.
Yeah, but if you take a look, one is the negative of the other. So we get this is equal to sigma r over 4 epsilon 0 r squared times 2r plus, right? Or you could say minus, you factor out a minus,
Well, there's a negative 2.
and you get r squared minus big R squared over r squared minus big R squared times a negative 2r. And that just becomes a, well, 2r minus negative 2r becomes 4r, right? So then we have that it's equal to sigma times r times 4r over 4 epsilon 0 r squared. And so what do we get? That this is sigma r squared over 4 epsilon 0 little r squared. Right? But what's sigma? Q over A. And what's the surface area? It's going to be Q over 4 pi, which R?
Big R.
This is so big R squared. Times R squared. Right. It's pretty sick, right?
That's just ridiculous.
We're not done yet. Because what did we just show?
We just showed that it could really correlate.
No, not for your real. Whoa, 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 whoa. Anywhere outside of the sphere. That's right. Anywhere outside the sphere. So this is. Anywhere outside the sphere, it looks like a point charge centered at the center, outside the sphere. So what else do we have to investigate? Inside the sphere. So what do you think? Do you think this is ridiculous, right? But guess what? None of the geometry changes inside.
Did Newton start this with gravity?
Yes, because everything is true here. Notice the charge aspect, right? You didn't know it was a charge until when? way at the end, I could have said sigma was the mass,
Yeah.
surface mass density, right? Everything would have been the same. The only difference is that our vector, remember our initial vector? Where would have our initial vector pointed? Yeah, in other words, as opposed to it pointing, as opposed to our vector pointing that way, right? If it was mass, it would point inward. All right, so now we're ready to go to the last piece, which is, that was the end for it outside. What is going to be the electric field if you're inside?
So that's if your little r is less than your big R.
If you're inside a spherical shell.
If your little r is less than big R.
Be careful. No, that is for it's when it's uniformly dense throughout, like the Earth. This is a shell.
Oh, this is a shell. Okay.
The whole point is that actually proves why it's going to be 1 over r inside. Because if it's 0 inside of a shell, what does that tell you? That the only mass or the only charge that matters is the charge that is enclosed. So if you're inside a shell, is there any mass enclosed or any charge enclosed? So we'll do this when we get back. Later, guys. Sure.
When you have a charge,
Yeah.
but your point is like here instead of in the middle, what would your L be?
Let me see it. Come by our school.
No, I'm soccer.
Oh, priorities.
I don't want to be in soccer. I tried to quit, and it didn't work.
That's fantastic.
Fire in the soccer
Yes.
field. I'll get you canned for sure. There, I found that there was a course for it
Don't
fabrication.
I'll get you